this morning. Okay, guys, I'm going to go ahead and share my screen at this time. And we're going to get going with our training this morning. And Tony and Luke, we should be seeing here pretty shortly you should be able to see a little PowerPoint presentation. We're going to do a little PowerPoint presentation this morning.
Yes, sir, I do see it.
Okay.
Yeah, we see it, Joel. It's not in presentation mode, though.
Yeah, it should be coming up here just real shortly.
Yep, thank you.
You all squared away? All right, fellas, again, this morning, this is going to be an airflow measurement overview. Now, one of the things I'd like to stress this morning, it's not a lot of lecture and not a lot of fluff this morning. This is going to be about a 1-hour program, 45 minutes to an hour based on our questions and the information you guys want to ask after and so on. But please, during the presentation, if you've got a question, please unmute your mic, ask your question, then mute your mic back up, or put it in the chat box again, and Tony and Luke are going to be monitoring that chat box. So this morning is airflow measurement. Again, not a lot of overview, not a lot of fluff or theory, so to speak, but really what this is going to be, how do you measure airflow? Really focused in on that. So we're going to be doing some basic things today. So today, as we review our basic airflow measurement program, the subject we're going to be talking about specifically are going to be using external static pressure. So we're going to talk a little bit about external static pressure and what it is, and the use of those factory airflow charts. So every one of our air handling or air moving pieces of equipment, it doesn't matter if it's a furnace, it doesn't matter if it's an air handler, it doesn't matter if it's commercial, it doesn't matter if it's residential. Every one of our air moving pieces of equipment that you get from our Winsupply folks and from our Champion manufacturing Johnson Controls is going to have an airflow chart. And so all those airflow charts are going to be based on external static pressure. So we're going to talk about external static pressure as a main method of measuring airflow this morning. In addition, we're going to talk about filter grill sizing based on manual D velocities. Now remember, guys, manual D is kind of the Bible, if you will, for residential duct design. So we're going to dig into some filter grill sizing, and I've produced a little quick sheet. And that little quick sheet, what it is, it's actually based on manual D velocities, recommended velocities across the filter grill, a return grill, and 80% free area. So let me stress that one more time. Okay, somebody's got their mic open, and we're getting a pretty good echo right now. So if everyone will go ahead and mute the mic, please.
Joel, I'm going to go ahead and mute the group, and then you'll need to unmute yourself.
Okay. All right, that sounds good.
Hang on just a moment here.
Okay, Tony, can you still hear me okay? Okay, Tony, can you still hear me okay?
Yes,
Yeah, we can hear you.
I can hear you now.
Okay.
Yep. So everyone else is muted. Yep.
That sounds good. Thank you. Anyway, so filter grill sizing will be based on manual D. That little quick sheet is based on manual D velocities, recommended velocities across the filter grill, and 80% free area with the use of that quick reference guide I just made reference to. And finally, towards the end of our training session today, we're going to review a temperature rise method of airflow measurement as well. So what it is, it's just a quick little application of some math and a temperature probe, and we'll show you how to do that as well. So today we're going to be, to summarize the welcome, today we're going to be learning how to measure airflow 2 different ways. So after today, I would hope that everyone will be equipped and ready to measure airflow at least 2 different ways today. Okay, so as external static pressure is the total static or the total air pressure in inches of water column measured on the supply and return side of a duct system. And so please remember, the fan is designed to move air through the duct system by providing a positive air pressure on the supply side and a negative air pressure on the return side. Now, to find external pressure, what we're going to do, we're going to take the following steps. Number 1, we're going to measure the supply side air pressure, which is going to be a positive pressure with the appropriate tools, and we'll talk about those tools in just a second. Step number 2, we're going to measure the return side pressure, which is a negative pressure. And then we're going to just add those values together. Now, fellas, I want to stress something. With today's tools, sometimes you have a 2-channel digital manometer or magnehelic gauge. Some technicians, they like to take the supply and the return air pressure together, like on channel 1 and channel 2 of their gauges. And that's fine to do that, but I highly recommend that you take the pressures individually. And here's why. If I measure my supply side pressure first, and then my negative pressure or my return side pressure second, and you don't have to do it in that order. You could flip-flop the order, but if you take those air pressures separately and then add them up, I believe, in fact, as I know, you get a better rating. And here's why. Because sometimes if you have a duct system that's providing some internal turbulence, and if you try to take those 2 pressures together, in other words, they're being read together on the gauge, what can happen, you can actually be in a situation where you're trying to average 2 turbulent air sources based on the duct system. So I've found in the field it works best to take one pressure first and then take the other one, because if you do it that way, when you're taking that air pressure by itself, the other side of the gauge, so to speak, is at the atmosphere, is atmospheric pressure. And so the atmosphere is very stable. It's just Mother Nature. And so if you're referencing your pressures individually to atmospheric pressure, you get a more stable reading. And the result will be you'll have a better overall reading, a more stable and accurate reading. So you guys do what you want to do out there, but you're going to see us today. We're going to be taking the positive pressure first. That's just the way I like to do it. And then the negative pressure on the return side, then we're going to add those together. And whatever that number is will be our ESP, or external static pressure. Any questions or comments so far? Everybody good? Okay. So let's talk about the tools to find external static pressure. Now, there's lots of different tools out there that you can utilize. I like to use just a digital manometer. What we're seeing right here, this is just a very common, it happens to be a field piece, but there's lots of good pieces of equipment out there. Fluke makes one, UEI makes one, Field Piece makes one. This is just an example of a digital manometer. You can also use what we call a magnehelic gauge, which is a large round gauge that reads in inches of water column. And if you're really old school, you can go back to the inclined water manometer, which is basically about 18 inches long, filled with water, and it sets on the side. It sets on its side, and that's kind of old school, but most everyone nowadays uses a digital manometer. So we're going to be featuring this digital manometer today as the featured tool for today. So what we're going to do, we're going to select which port we're going to use, P1 or P2 on this particular tool. And so we have 2 ports. We've got P1 and P2 on this particular tool. So we're going to select which one we're going to use. This next thing we're going to do is, once we hook our hose up and our static pressure probe, we're going to go ahead and zero the meter. So you can see there's a place to zero the meters, so we get an accurate reading. The third thing we're going to do, we're going to make sure and attach our hose to the selected port, whether it's P1 or P2. And the other end of that hose is going to go to what we call a static pressure probe, a static pressure probe. Now, this is a special probe for taking static pressure. And so we'll be looking at that in just a moment or two as well. So the static pressure probe, as you can see, is used to provide static pressure to the manometer, or to the digital manometer. Now, please note the airflow must be into the pointy end of the probe. And I like to always stress this because we want to make sure that we position this probe. You'll notice this probe is bent 90 degrees. And by the way, they come in different lengths. And so good practice is you put this in, and you also notice that on the static pressure probe, it has a magnetic base to it. So you can snap it on to a metal ductwork if you have metal ductwork. If not, you're just going to have to hold it. If it's like duct board or flex duct, you'll have to just hold it into the airstream. But you always want to make sure that pointy end, that you'll see the 90 degrees there. Make sure that pointy end is going into the direction of airflow. That's really important as you take a look at that graphic. The other end of the static pressure probe is going to be hooked up to a hose that goes to the manometer. So basically, you're going to have your digital manometer with a hose going to this static pressure probe. You'll poke a hole in the ductwork. You'll poke a hole in the supply plenum and the return plenum. And then you'll actually read the static pressure or the pressure of the return and the supply air. Now, this is really, really important. Please make a note of this. Write this down. Put a smiley face by it, whatever you have to do to remember this. If you have a filter, in the return ductwork right next to the air handler, make sure you take readings on both sides of the filter. Let me say that again. I like to take readings on both sides of the filter because that gives me some idea how much static pressure drop or how much static pressure difference I have across the filter. If you have a filter like in a return grill and the ductwork comes down and hits the air handler, go ahead and just take it in the return ductwork, because what you'll be doing is you'll actually be able to read how much pressure that filter is actually adding to the return static pressure. And so you'll see in our graphic here in a minute how we have that hooked up. So basically, this would be a good example right here in this first graphic. You'll see our static pressure probes in the supply duct and in the return duct. Well, if my return air filter is downstream from the air handler, maybe in a closet or something, or, in a hallway somewhere, what we're reading right now is the total static pressure, including that filter. Now, let me stress one more time, if the filter's right next to the air handler, be sure and take pressures on both sides. That way you can get a really good idea of what kind of pressure drop you have across that filter. So basically what we're going to do, fellas, we're going to measure our supply side static pressure, step number 1. And then step number 2, we're going to measure our return side pressure. And then step number 3, we're going to add those pressures together to find external static pressure. So any questions or comments on the basic steps and the tools we're going to be using to find static pressure as we start looking at taking some actual measurements and looking at some airflow charts will be our next little session here. We'll be looking at airflow charts and comparing static pressure to airflow correlation on the charts. But we want to make sure everybody understands the tools before we get into that. Any questions or comments so far?
Yeah, what do you do like in a situation where there is no drop down return? It's just like on a stand with a filter through the wall, or actually a filter under the unit.
That is such an excellent question. So everybody watch my cursor right here. I know it's kind of hard to see my cursor, but if you see my cursor, what you're going to do, let's say this air handler is just sitting on a stand. Well, the fan is going to be inside this air handler. So what we're going to do, we're going to take the static pressure probe and we're going to turn it into the air that's coming into the bottom of the air handler, so what this pressure probe is doing, we're basically reading how much the fan is sucking against that pressure probe. And so that's the idea. So we want to see if this air handler is just sitting like on a box, we could actually poke a hole in the cabinet of the air handler and make sure that pressure probe is pointed down into the airstream, and we'll be reading how much suck that fan is pulling against that pressure probe. Does that make sense? So it's perfectly fine to poke. It's perfectly fine to poke a hole right here in the air handler, like on the side or whatever, and read it that way. That's perfectly fine. Good question. Any other good questions or comments?
I have a question.
Come on.
What if I remove the front plate and put it in the plate of the coil section? The front plate of the coil.
He's saying to put it in where the blower is. So if you have
he's saying here.
Yeah, but that's at the bottom of the blower.
Guys, you got to remember. On an air handler, you're gonna have your fan. Your coil will actually be in the air handler.
Yeah, the coil's on the bottom, fan's on the top, most units.
Okay, and that's fine. So what you're gonna do, you're gonna take two readings. Poke a hole so that you're reading just the fan, and then poke another hole above the coil so that you can see how much static pressure drop you got across the coil, if that makes sense. So you
Okay.
can,
So you just want, so you want one in the coil or do you want one by the blower? In your scenario, are you going by a blower that's, under at the bottom, like a positive?
all right, so let's say, for instance, in this air handler right here, let's say that, look at my cursor, let's say we have the coils right here, and then the fan is below the coil. Then just poke a hole in the cabinet so that you're reading the maximum suck of the fan. And that's,
Yeah,
and
so
that's really-
that's why they're a little confused, because most of our air handlers are negative, so you're going off a positive, right? Like if the
So
blower was on the bottom.
So on the supply side, if you got your fan here and your coil here, you're going to be reading supply side pressure.
All of
Now,
our,
one of the things I like.
After the coil.
Well, yeah,
go
what
ahead.
he's saying is all of the air handlers are negative because the blower's on top. That's why they're confused.
That's perfectly fine, because you got to remember, an air handler includes the coil as part of the static pressure reading on the chart. On a furnace, the coil's not included on that chart. So you have to go underneath the coil on a furnace. But on an air handler, it's included. So if you'll go on the return side here, like I said, and depends on your manufacturer. I mean, if you've got a negative pressure, to your point, a negative pressure air handler, you'll have the fan, then you'll have the coil. But most manufacturers, us included, the coil is part of that static pressure chart. So you're just remember this is the easiest way to remember it. You always want to read the maximum suck on the fan, whatever is going to provide the maximum suck. So if I've got a, look at my cursor, if I've got a filter right here, I'm going to take that static pressure probe and put it on the back side of the filter. If I've got a return air filter up here, maybe where this arrow's pumping on the return, and I've got a filter up in the ductwork somewhere, I'm going to put it right where it is right now. Because we always want to read the maximum suck against the fan on the return stem.
Okay, so you want one in where the for the static pressure probe on the supply, you want it in the fan section, not before the coil.
No, you're on an air handler, you're going to want it on the supply side, you're going to want it right into the supply pump. If it's a furnace, you'll go underneath the coil because the coil is not included on the furnace, on the airflow chart.
Above the coils, yeah. It's gonna have more sucking through the coil.
That's what I had, that's why I'm asking. He says the coil is included, so it would be in the fan compartment.
Yes.
On a negative pressures, on a negative system, it would be in the fan compartment, not in the coil section.
Yes.
For your return reading, correct?
That is correct.
Okay.
Yeah. And then because an air handler has a coil and a fan built in, we're always going to put on an air handler, we're always going to put our static pressure probe just right in the supply duct, right in the supply plate, and poke a hole and have it pointing right into the airstream as it comes off the air handler. Good questions. And any other good questions or comments? Everybody good? Excellent. Yes, please keep those good questions coming. So in summary, one more time, on an air handler, we're reading supply pressure right in the supply duct, and we're going to position the return static pressure probe, and we're going to point it into the airstream where it's going to be reading the maximum suck that fan is pulling against the ductwork and or filter if it happens to have the filter in there. Okay. So let's take a look at some airflow charts for an air handler. So this particular air handler here, we know we've got a lot of capacitor style air handlers out there yet, AHR air handlers. This is a very, very common air handler. And by the way, every manufacturer should give you some sort of airflow chart. This happens to be our AHR air handler, which is a capacitor style air handler. We know there's a lot of them out there yet. So the way this chart works is this. So first, step number one, we have to determine, we take a look at our chart and we determine which model of air handler we're measuring the airflow on. So we measure that, or we take a look at that and actually look at the data plate and see what air handler we're dealing with. Step number two, if applicable. Now, some air handlers, if they're a capacitor style air handler, there's actually going to be two charts. There will be a 208 volt chart and a 230 volt chart. So if it's applicable, your manufacturer, They may or may not do this, but we do on our capacitor style air handlers or older style air handlers. If your voltage is closer to 208, you use a 208 volt chart. If it's closer to 230 volt, then you use a 230 volt chart. It'll make a slight difference in the amount of airflow that you're actually seeing. So determine voltage if applicable on your airflow chart. Step number 3, determine what speed tap you're on. So physically look at the motor and see what speed tap you're on that you're testing your airflow. So whatever speed tap that is. So let's say it's high speed tap in this example. You'll then go over and you'll look at your external static pressure that you measure. And then you'll come down and you'll correlate with the air handler and the speed tap on the appropriate chart, based on voltage if applicable, and you'll read your CFM. So in this example here, so let's back up one more time. So I have an AHR 24B air handler, and I actually take my voltage rating on the job, and I see this 212 volts. I'm just making that up. So I'm going to use a 208 volt chart. I take my static pressure reading. I see that I'm on speed tap number high. I'm on the high speed tap. I've got 0.50 inches of static pressure total. And I correlate that down, and the actual airflow I'm moving through that cabinet is 925 CFM. So let's go ahead and as we're referring to that chart, those charts, everyone should have some little charts that we sent out earlier a few weeks back. So let's say, for instance, we have an AHR 30B. It's on a medium speed tap, and we're looking at the 208 volt portion of that chart. So we see as we take a look at our digital manometer and our static pressure probe, the AHR 30B on medium speed tap, we correlate that on the chart, 208 volt section on the airflow chart. And we see our first reading is a 0.32. So the supply static pressure is a 0.32. And so I either write that down or I just remember it. And again, guys, I like taking my supply static first and then my return static. That's just how I do it in the field. And I take them separately, even though I have a 2-channel digital manometer, because I believe you get a more stable reading and a better reading if you take them separate and add them up. So that's how I like to do it. So 0.32 is our static pressure on the supply. Write that down. I then go to the return and I see I've got a return static pressure of a 0.18 inches of water column. I then now take those two readings. So I had a 0.32 and a 0.18. And so let's add those up. I see that I've got a 0.18. Again, write that down or just remember it. I then add those values together. So the external static pressure is going to be 0.32 plus 0.18 equals a 0.50. Now, guys, you don't have to, this is important. You don't have to add, you don't have to do algebra to add these up and errors, even though the 0.32 is a positive pressure and the 0.18 is a negative pressure. You don't have to do algebra and say, well, what's a negative and a positive? No, you just add the whole numbers up. Let me stress that again. You just add up the whole numbers. So it's 0.32 inches of static on the supply point. It's a negative 0.18 static on the return. You just add those up for a total static pressure. In other words, it's the amount of total pressure that fan is sucking and blowing against the ductwork and all the registers and the filters and stuff like that for a total of 0.5. So referring to the chart, what is the CFM? So again, an AHR 30B medium speed tap on the 208 portion of the chart, 0.5 inches of static. What is the CFM? Does anybody have that? Put it in the chat or unmute your mic and tell me what the CFM would be under those conditions. Okay, if you're reading the chart properly, it should read 890 CFM. There you go. So this is a 2.5 ton air handler, medium speed tap. It's probably on a 2 or 2.5 ton unit. If it's matched up with a 2 ton unit, we're blowing a little bit more airflow than we normally would because we want to always build our duct systems, fellas, to provide 400 CFM per ton. And so if we had this on a 2-ton unit, we're blowing a little bit too much. If it was on a 2.5-ton unit, we're a little bit light on airflow. So you guys get the idea. So 400 CFM per ton is the nominal airflow we're looking for based on the tonnage of the outdoor unit. So this is a 2.5-ton air handler, but it could be matched up with a 2-ton unit outside, based on the application. And so we're actually blowing a little bit more air than we need for a 2-ton unit. Any questions or comments on this first example? We're going to do several more just to make sure everybody's squared away with this. Any questions or comments?
Yes, good morning. I got one question.
Come on.
So the illustration that you have here, blower on top, coil on the bottom, that basically describes most of our air handlers around here.
Yes, sir.
And in this illustration, our probe placement was in the return duct drop and the supplied plenum.
Correct.
Okay. Earlier, I believe, unless I misunderstood it, that if it were an open return, we would be taking our return probe and putting it after the evaporator coil into the cabinet of the unit. Is that what you would recommend?
That's an excellent question. So if you actually have an open return, literally an open return where there's no duct work at all on the return, what you would do is you'd literally take look at my cursor, you'd literally take your MagnaHelic and your MagnaHelic probe or your digital, your static pressure probe, and you'd stick it in right here underneath the coil. Or you'd stick it in, because remember, on an air handler, on our equipment anyway, the coil's included on that chart. So you'd poke it in right into the cabinet just beneath the coil with it pointing down, so it's sucking, so it would actually read the suck across that. Now, we normally don't see air handlers where they're just wide open like that, but if you had a situation, let's say this was sitting in a closet and it had like just a wooden box around it, you'd poke a hole in the side and put that static pressure probe in, so it's coming down right below that coil, again, where that pointy end of that probe is sticking into the airstream. Now, remember, on an open return like that, you're not going to see probably a huge amount of static pressure because it's just open. But if you did have that situation, you'd still put it in underneath that coil, because the coil is included in the cabinet on an air handler. Good question. Does that make sense?
I think the point of confusion is coming from, maybe it's not an open return. Maybe the return is boxed in, but the filter, though, is at the air handler itself.
Oh,
so,
okay.
And that's where earlier I thought that I'd heard you say at that point we're to penetrate the cabinet, but then that would be after the evaporator coil.
Yeah, and that would, so what you're going to want to do, let's say you actually have a filter in here. Come into the side of the cabinet and sneak a hole in, at the edge of the cabinet where it's convenient, and actually stick that pressure probe right underneath the coil, to where you can read how much the fan is sucking against that filter, if at all possible. You understand what I'm saying? So let's say I had a filter right here. Let's say I had a box and I've got the filter. Look at my cursor. Let's say my filter is right here at the edge of the cabinet. I'm going to come over here and I'm going to poke a hole in the cabinet below the coil, so I can actually read that static pressure where it's sucking against that filter as well. Does that make sense?
Now that makes sense. What you're saying, if the filter was installed on the side, like if it were a furnace with a filter rack.
Yeah.
We're in the South Florida. Well, I'm in the South Florida market, and our filters are actually installed in the air handler itself.
Okay.
So it's directly underneath of the coil where there's not much room to do anything.
Okay. So an alternate probe. Now we didn't talk about it, but an alternate probe that works pretty good. It's not as accurate as like the static pressure probe I just showed you. Is just a straight piece of tubing. And if you use just a straight piece of tubing, take like a little 1/4 inch or 1/8 inch piece of tubing and poke a hole in the cabinet right between the coil and the filter and slide that in there, because we want you to read the suck that fan is pulling through the coil and that filter. And so that's an alternate to use what we call a straight static pressure probe, but it's not quite as accurate as the little, you know, on the tool itself, because it's got the little holes on the side and all that. But if you get in a situation like that, just take like a little 1/4 inch piece of copper tubing, or a 3/16 inch piece of copper tubing, a straight probe, drill a hole right here in the cabinet below the coil, but between the coil and the filter, and sneak that in so it's just about in the middle of that coil, so that you're reading, the optimal air going through that coil, sucking across the filter through the coil, because it's really important on an air handler that the coil is included on that chart. Because if you come up here and you poke a hole in the cabinet above the coil and you're reading the suck of the fan above the coil, what's going to happen is you're going to have an inaccurate reading on the chart.
So I mean, like in a real world situations, there's tons of applications where they're on a free drawing metal stand in the closet, and we're not getting to 3 sides of that to drill a hole and stick a tube in.
Okay.
So where do we do this at? And then some units, say it's a different unit, like a ream, where it doesn't have a built-in filter rack. There's no place to drill in. You're just going to drill right into the pan.
All right. So
That's not realistic in the field.
all right. So what I would do in those situations, because that's a unique application. So what I would do in those situations, I'd make sure I had an absolutely clean coil. In other words, you want that coil clean, clean, clean. Now this is and I hate saying rules of thumb, because it can vary so much on manufacturer. They have an N coil, a W coil, an M coil, a coil, whatever, a slab coil. However, most manufacturers will tell you that their coil, clean and wet. Now, let me stress that, clean and wet, will typically have about a 0.2 inches of water column static pressure. So if you absolutely can't get anywhere, anyplace else, go ahead and poke a hole above the coil in the cabinet, read what the fan is sucking, and then add about a 0.2 on top of that for a wet coil. And again, this is kind of generalized. I don't normally like talking about generalizing or rules of thumb, because every manufacturer is different. But typically, most manufacturers, residential application, if the coil is clean and you've got condensate running down the coil, you can figure they have a static pressure drop across the coil of about 0.2. Does that make sense? So in other words, if I come over here and I poke a hole in the cabinet above the coil, and I read a 0.2, then add another 0.2 for the coil for a total of 0.4. You with me?
Yeah, that makes sense.
So that would be the only way you could do that. Because remember, on our equipment, other manufacturers, they may not include the coil, but on our equipment, on the Champion equipment, Johnson Controls equipment, the coil's included on that static pressure airflow chart that we're talking about.
So if you had the N coil on your equipment, we could get underneath where, say, the top part of that coil is, and that would be accurate without adding the 0.2. Like if it was an N coil.
Yeah, so if you anywhere underneath that coil.
Okay.
So if you can, drill a hole and sneak underneath the coil and poke just poke a straight tube in there, or the little static pressure probe, that would be ideal, because that works the best. But if you've got duct work coming to it, like we're showing you here, you could, this is just kind of illustrating if you have duct work in like a return grill up here someplace, or you have multiple returns on a piece of equipment. And so what we're doing is we're basically, just taking that static pressure. But yeah, if you go underneath that coil with just a straight tube, that's acceptable. Good questions. Any other good questions or comments before we continue? Okay. Well, let's go ahead and do another couple examples. In this second example, we've got an AHR 36B. It's on high-speed tap, and we're on the 230-volt portion of that factory airflow chart. So this is just another AHR example on an air handler, high-speed tap, 230-volt, portion of the chart. And on this first reading, it looks like we've got a 0.61 on the supply, which is fairly high, but we have a 0.61 on the supply. And so go ahead and write that down, fellas, or just make a note of that, a mental note, or write that down. On the return, we have a 0.18. And so we add those together. And we see that a 0.61 plus a 0.18 is a 0.79. Now, fellas, you're going to notice something as you take a look at the airflow charts. You're going to notice that we start getting into some gray areas. When I say gray areas, or the chart may run out at like 0.8 or 0.7 based on the chart you're looking at. Some charts go up to go up to 1.0. So based on the product you're looking at, we see that 0.79 on this particular chart, we're crowding the end of the chart. We may even be off the chart. And so it's important that we note that if we have this type of static pressure, we have some issues with the ductwork. And so this is another reason I like to take the readings separately, because right now on this one here, the obvious one is the 0.61. That was supply. So somewhere on that supply, maybe we have a kink in the supply duct. Maybe it's some duct board that's folded in. You could have a situation where grandma has some rugs or something thrown over the supply registers, whatever. So you're going to need to investigate, because you've got pretty high static pressure, very high static pressure on the supply, in this case of 0.61. So the 0.79, as we take a look at our airflow chart, an AHR 36B on high speed tap, 230 volt, what is our CFM? Does anybody have the CFM off that chart at 0.79? So we know something. We know that it's going to be less than 880 CFM because the chart runs out. It's off the chart. And so I wanted to do a couple examples like that with you today, because if we get in a situation and we're off of our chart, then we know that we have some remediation to do. We need to start investigating and finding out why that supply duct, in this example, why that supply duct, maybe the TV guy was up in the attic or whatever, or something happened and the supply duct is collapsed. Or if it's on a brand new installation and you're starting the thing up, you have grossly undersized supply duct. And so please keep all that in mind right now. And so this is kind of part of a airflow and duct design class that we've taken out we're showing you how to measure airflow, but it's really important that we start investigating as to why we have such high static pressure. Any questions or comments on that second example? Okay. I'll tell you what, team, let's go ahead and do a couple examples with the AE air handler. The AE air handler is a high efficiency blower motor, and we have a lot of those products out there as well. And on the AE air handler, you'll notice that there's no voltage. It's just static pressure and model. So take a look at your AE air handler airflow chart, and we see that we have an AE 18B. So it's a 1.5 ton air handler. We're on high speed tap. We noticed our first reading off our digital manometer is a 0.32 inches of water column. So please write that down or make a note of it mentally. 0.32. And then our second reading on our return is a 0.14. 0.14. So we have a AE 18B high speed tap number 5. 0.14 on the return static. And so we add those values together. We have a 0.32 plus a 0.14 that gives the total static of a 0.46. So as we take a look at that chart, what is our CFM on that 1.5 ton air handler, that AE air handler, high speed tap, 0.46 inches of static? What's our CFM off that chart? Anybody?
$1,053.
man, give yourself a star. That's close enough. I had 1,040. That's close enough. If you're, because it's kind of falling in between there. So what you're doing is you're kind of extrapolating a little bit. I had a 0.46. I had 1,040. But if you had 1,050 or 1,053, that's close enough. Because remember, team, if you're within 10 or 15 CFM from the chart, you're close enough. Any questions or comments on how we did that from anyone on the team? Put it in the chat box if you've got a question, or just unmute your mic if you've got any good questions or comments. Okay, let's do one more example of air handler using the static pressure probe, and then we'll go ahead and jump into another method of measuring airflow using, it's kind of an older method called the temperature rise method, but let's do at least one more. And in this fourth example, we have an AE36C. So this is a 3-ton air handler, and it's also on high-speed tap. And so we notice that on the supply side, we've got a 0.57 inches of water column, which is pretty high. And so you go ahead and write that down or make a note of it, 0.57. And fellas, you're going to notice something too. Another reason to take these pressures individually is it helps you remediate or figure out where your problem is on the ductwork, if you've got problems on the ductwork. So by taking the pressures individually, supply and return individually, it can help us break down which side of the fan are we having issues with, on the supply side or the return side. Now, I find that most of the time you're going to have issues on return. You just don't have enough return air on the job site. But sometimes you'll have undersized ductwork, or you'll have issues on the supply side as well. And so in this example here, maybe the company ahead of you, or maybe the system's 10 years old, and a lot of different companies have worked on it. And so the technician goes out and he puts it on high speed tap, and he's blowing whatever air he can blow. He doesn't really understand maybe what's going on, a previous company looking at it. And then you guys come in with your tools and all that, and you start taking measurements. Say, golly, no wonder they're having issues. We're not moving enough air. And so it's important that we understand, what we're looking at when we look at static pressure. So in this example, we have a 0.57 on the supply and a 0.18 on the return. So we can see right now that the majority of static pressure on this job is going to be on the supply side. And so let's go ahead and take a look at that. Our external static pressure, or ESP, is 0.57 plus 0.18 is a 0.75. So taking a look at your AE36C airflow chart, we're on the high speed tap. We've got a 0.75 inches of static. And so that's very high static pressure. Most air handlers are designed to operate between about a 0.3 and a 0.5 total static. It's kind of the sweet spot on them. And while I'm thinking along that line of thinking, while you're taking a look at this air handler static pressure, our new air handlers that we're launching, in the process of launching, are actually tested at 0.5. So that's kind of neat. So our new air handlers have a more robust fan in them, and so they're actually tested at a higher static pressure. So anyway, back to the session here. At a 0.75 inches static, what is the CFM on that AE36 air handler on a high speed tap? 0.75. Anybody, go ahead and unmute your mic and let me know what the airflow is on this final example. I'm glad that the mics are kind of muted, because the truth is the chart runs out again. We know the airflow is less than 1348 because that's where the chart runs out. And so I just wanted to do one more example of this. If you have a sample or an example where you have a duct system and you're in there and you're measuring airflow, you say, daggone, the chart runs out, you've got a problem. And so by taking those pressures individually, again, you can tell quickly which side is it on, supply or the return side of the duct system. Any questions or comments on how to use the factory airflow charts and applying the proper tools, the static pressure probe and a digital manometer in this example. Any questions or comments on those tools and how we're going to use them as we start going into taking airflow measurement, kind of an old method called temperature rise. But before we get there, are there any questions on what we've talked about so far? Everybody good? Tony, unmute your mic for me quick. Can you still hear me okay? Is everything looking okay on the presentation?
Yep, loud and clear, Joel. Everything is going well. There's nothing in the chat, so go ahead and proceed.
Got it. Thank you. All right, fellas, what you're going to notice here, one of the little handouts that we shipped out or sent out a few weeks ago is a quick reference guide. This quick reference guide are some predetermined return filter grill sizes. So this is a return filter grill. And so we see a lot of that in some of our market areas, especially down the Florida area. You guys probably have a lot of return grills that actually have a filter in them. So according to Manual D, if that return filter grill has a filter in it, you're going to have a maximum of 300 feet per minute grill face velocity is what Manual D recommends. In addition, unless you have some special grills that have got, that are made of wood, those are very, very inefficient. They're only about 25 to 40% efficient. If you have some real high-end grills, they might be as high as 95% efficient, what we call free area. But your standard return grills typically are about 80% efficient as far as the amount of air that will actually move through that grill. And so based on an 80% free area of that grill and 300 feet a minute grill face velocity, that's the maximum velocity Manual D recommends the air moving across the filter. If you got a filter in that grill, they don't want you exceeding 300 feet a minute velocity, feet per minute, across that filter. The higher the velocity, the less efficient that filter works. And so based on all the Manual D criteria I've just mentioned, this is a quick sheet to help you say, well, gee, I wonder what a 20 by 20 filter grill, how much air you're actually moving through that thing. And you'll see that in our example here, this is right out of Manual D, a 20 by 20 filter grill at 300 feet a minute velocity and 80% free area is going to be good for about 650 or 670 CFM. A 24 by 30 would be 1200 CFM and so on. So we wanted to provide this to you as well. These are already been figured out for you. And so if you've got a 24 by 24 grill, you look on here and you say, well, gee, was a 24 by 24 is good for about 960 CFM based on Manual D recommendations of 300 feet a minute maximum grill face velocity and 80% free area. So just wanted to kind of equip everybody with this. This is just a little quick reference guide that'll help you size filter grills at a glance. So any questions or comments on this little quick reference guide we provided to you as well? Any questions on that?
Yeah, Joe, we have a question from Curtis. What if your static pressure is good, but the customer isn't getting enough air to a room? But in order to cool that room, it puts the static in the gray area.
What I'm going to recommend, I mean, if your total static is good through the system, remember if you put a larger ductwork, if you put a bigger takeoff, in other words, into that room, you'll actually provide more air. The other thing that you can do if your static pressure is good, for the entire system, you can go ahead and put manual dampers, if possible, on the other takeoffs and start balancing it with some manual dampers. That would be a way to help remediate that or to push a little extra air into that one room. But the best thing to do if you need more air into a space, more volume, is to increase the takeoff duct size into that room is the better way to do it. Good. That's a good question. Any other good questions or comments?
Yeah, I got one. So we use our chart we find out that we got, higher than desired static pressure. It drops our CFM down below, the 400 CFM per ton rule. Is that going to have an effect on capacity or efficiency or both?
Oh my God, that is an absolutely excellent, timely question, and the answer is yes to both. So on the air side, and sometimes, guys, I get a little bit preachy on this because I'm really adamant about proper airflow. But I mean, if you're anytime you reduce airflow for whatever reason, whether it's because of undersized ductwork, pleated filters, dirty evaporator coil, I mean, any of that stuff, it reduces capacity of the unit. And not only does it reduce capacity, but it also decreases the ability of that unit to remove humidity and so on. Now, if your airflow falls anywhere between about 350, 375 to 400, I'm not going to sweat it. But if you start getting down to below 350, especially if it's high static pressure, it's going to be noisy, and it's going to be, you're not going to be able to handle humidity like it should and all that. But yes, to both questions, it'll give you, or both comments, it'll give you reduced capacity and a reduction in the ability of the of humidity control and all that. And remember, guys, the larger the duct, the lower the velocity and the quieter the system. Now, you don't want to get too large, but the point is there are target velocities in those duct components that we will certainly talk about in our airflow class. This is just how to measure airflow today. Excellent question, though. Any other good questions or comments? Okay. Well, fellas, another method of measuring airflow. This is kind of an old-timey method. This is actually how I learned it as a young technician. But all you have to have to measure airflow with this methodology is a temperature probe, an accurate temperature probe, and an amp probe and a voltmeter, which you're going to have on your truck anyway. So here's how this formula goes. CFM is equal to the output in BTUs of the device divided by 1.08 times delta T, and the delta T portion of that is the difference in temperature between supply and return air. Now that sounds like a mouthful, but let's talk about this formula a little bit. CFM is equal to the output of the device in BTUs divided by 1.08 times the delta T, or temperature difference between supply and return. So what we're going to do when we apply this formula here, and like I said, it's very, very simple. And once you do it a few times, you'll see how simple it is. So number one, we're going to energize the heat strips on this air handler. And we're going to make certain that we're on the desired airflow call. In other words, we're going to select whatever speed tap we're testing. And so whatever speed tap you're testing, make sure the fan is blowing on that desired speed tap. We're going to energize the heat strips and make certain that we're on the airflow call is present that we want, and the compressor is off. This is huge. You don't want the compressor on. So you're going to shut the disconnect off outside. You're going to select the speed tap that you want to test on the air handler. You're going to energize the heat strips, and you're going to run the fan with the heat strips energized with the compressor off outside. Step number one. Step number two, you're going to multiply the measured voltage times amperage. Now this is huge. So you're going to measure with the fan running and the heat strips running. You're going to measure the voltage with those components running, the outdoor units off. You're going to measure the voltage and the amperage, and you're going to multiply volts times amps times 3.414. Now that 3.414 is a mathematical constant to convert wattage into BTUs. So volts times amps equals watts times 3.414 equals BTUs. And that gives you the output portion of that formula. And so volts times amps times 3.414 equals the output of the unit. So you write that down and mark it down or remember it. Step number three, you're going to measure the supply air temperature and the return air temperature And then what you're going to do, and we recommend do this within about 3 feet of the air handler, because you don't want to have the heat strips, cooking directly against your temperature probe. So go about 3 feet down the supply duct, and if you can't do it at that way, then go to your very first supply register for the supply temperature. And so anyway, try to be about 3 feet from the air handler on the supply temperature reading, because again, the heat strips can kind of give radiant energy and throw off the temperature probe a little bit. So measure your supply and return air temperature within about 3 feet of the air handler, and then find the difference. That's the delta T portion. Find the difference between supply and return air temperature, and then multiply that difference by 1.08, and then find the result of that. So let's say the supply air temperature is 70 degrees, 120 degrees. A return air temperature is 70 degrees. The difference would be 50 times 1.08, whatever that is. And that would be the bottom portion of the formula. Guys, it takes a lot longer to talk about it than it does to actually do it. We'll do a couple examples here in a minute. Step number 4, you divide the output of the device, the top part of the formula, by the result of step number 3, and that gives you CFM. So let's do a couple examples. So take your calculator out for me, and we'll kind of walk through this together. And so I've got my calculator out as well, my little handheld calculator. So in this first example here, this is a 2-ton unit. I get the thing running. I make sure the outdoor unit is off, and I've got 249 volts. That's my actual measured voltage with this thing running. I take my amp probe and I snap on there, and I see that my amperage is 33.6. So if I take 249 on my calculator times the amperage of 33.6 amps, and then multiply that times 3.414, that should give me an output in BTUs of around 28,500 and change. So go ahead and use your calculator again to kind of follow along if you want. So 249 volts measured voltage times 33.6 amps times 3.414 equals 28,563. So now write that down, or remember it, but that's the output. So in this example, the output is 28,563 BTUs. Now watch this. I take my temperature probe, and I see that my supply air temperature is 105 degrees in this example. My return air temperature is 72 degrees. So I find the difference between 105 and 72, and that should give us 105 minus 72. That gives us a difference, a temperature difference of 33 degrees. But hang on a second, we're not done with that yet. So we take that 33 degrees times 1.08, and that gives me a number of about 35.6. That 35.6 is the number that goes on the bottom of the calculation. So let's write that down, 35.6. Now, to complete this formula, fellows, what you're going to do, you're going to divide the output times that 35.6. So our output, remember, was 28,563 divided by 35.6. And that gives us a CFM in this example of 802. So this is what we call the temperature rise method, fellas. This works very, very well. This is kind of an old-timey way of doing it. I sent along with our printed information a few weeks back when I sent that information out. You should have a quick formula guide that's on there to remind you. But this method of airflow measurement is, like I said, it's kind of an old-timey method. But it says that if you know the output of the device in BTUs and divide it by 1.08 times the temperature difference of supply and return, that equals your CFM. And by the way, this is going to get you very, very close. If you don't have any other tools on your truck except a temperature probe, a voltmeter, and an amp probe, you can still measure airflow on a unit. Any questions or comments? We'll do one more of these examples here, but any questions or comments on the steps on how to achieve finding airflow with the temperature rise method?
Joel, there's a question from Brandon.
Sure.
While reviewing the return filter chart, he found he did some basic ductulator calculations on some of the square dimensions, and they were different from the chart, even taking into account the drag from a filter. Is there a formula for how these were calculated in the chart?
Absolutely. So what we did, let me go ahead and back up with that. I'll pull that chart for everyone. So let's do an example. Let's say we have a 12 by 12. This is just a real quick example. 12 times 12. That's 144. That's 1 square foot. Let me back up. So 12 times 12 is 144 square inches divided by 12 gives us 1 square foot. 1 square foot times 0.80, which would be 80%, times of the velocity of 300 feet per minute. So let's take 12 times 12 equals 144 square inches, and we always have to get to square feet. And in this example, we divide by 12. That gives us 1 square foot. Okay, so so one more time, 12 times 12 equals 144, and then divide by 144 to always find. You always got to get to square feet. So to take any number square inch, you divide by 144. That gives you the square feet. So in this example, that's 1 square foot times 0.8, which is 80% free area, equals 0.8 in this example, times 300, and that gives you 240 CFM in that example. Let's do another one. Let's do one that isn't quite so obvious as 1 square foot. Let's take a 20 by 24. So a 20 times 24 equals 480 square inches. We then divide 480 square inches by 144 to get square feet, because you always got to get square feet, right? You always have to get to square feet. And that gives us 3.33 square feet times 300 feet a minute velocity, face velocity, equals 1,000 in this example. So so that's how we did it.
And guys, I would add to that, you may want to get on Hart and Cooley's website or Lima, one of the manufacturers of grills, and they will have charts on all of their grills. There's different spacing, fin spacing, 1/3 inch, and 1/2 inch and so forth, and commercial grills and what have you. So that's maybe a easier way is to just print out, on the grills that you use, and most of what you find out in the field is I think it was called 1/3 inch spacing, something like that, and so you can find charts on that. We've all been on calls where the return air grill would be singing, and what causes that is too high face velocity. Joel has this at 300. In the manuals published by the grill manufacturers, you'll find different recommendations on face velocities for different applications, and so that's real helpful.
So, and so to Tony's point real quick too, the 80% free area is an average that I used when I developed this chart. That's an average of all different grills, return grills that we happen to have in our inventory. This is, I generated this back when I was in distribution myself. So to Tony's point, if you go to Hart and Cooley or you know, Cook or whoever, and you look up a particular return grill, it may say something like K of C or K of A, and it might be 92%. So you, instead of using a 0.8 in the formula, you'd use a 0.92. So that 80% free area is just an average of grills that we had in stock. We just averaged them up as far as the K of A. But if you go to Hart and Cooley or whatnot, and you look at a particular return grill and it says, you know, K of A or K of C, which is the free area, and it says 0.95 or 0.92 or 0.89 or whatever, you would substitute that 0.8 that I have for free area that in the formula. However, I want to really, really stress something. Even though a return grill might be rated for 500 CFM of face velocity, that is not with a grill in it. I mean, excuse, that is not with a filter in there. And so manual D, even though you might have a Hart and Cooley return grill, it says, well, our recommended face velocity is 450. If you put a filter in that grill, then it goes back to that 300. So that 300 is a hard, solid manual D number that kind of trumps even a filter grill manufacturer, because what I'm trying to say is manual D says do not exceed 300 feet a minute velocity across that filter. And so that filter criteria on that 300 feet per minute has to do with the filter, not so much the grill. So please keep that in mind, you know, and that's maximum recommended filter face velocity according to manual D. So by all means, if you've got a different grill than 80% free area, by all means plug that formula in. But this little chart that I gave you, by the way, if you will figure 80% free area, this is conservative. Now, if you figure 80% free area and 300 feet a minute velocity, that like we're talking about there, you will never get in trouble with this filter grill. And let me say that one more time. If you'll follow these recommendations on this little quick chart, this quick reference, if you provide return air grills and with filters in there, according to this quick reference, you will never get in trouble with undersized return grills. So that's just a little, that's hard-learned experience here. That's 25 years of building duct systems and finding out that manual D really does know what it's talking about. So good. Any other questions or comments before we do one more temperature rise measurement? Any other good questions or comments?
Yeah, can you go back to your temperature? There you go. So let's say that I've got one of these applications that I've been speaking to this morning with my filter inside of my air handler, and it's nearly impossible for me to get a return static pressure.
Okay.
Let's say that I have my manufacturer's blower performance data, and I have my formula, and I've worked out my CFM.
Yes, sir.
Could I take that CFM back to the blower performance data chart and then cross-reference that to determine static pressure?
That's an excellent question. I've not tried that. Thank you for that good question. I've not tried that. So so you're basically you've taken your temperature rise, you know what the CFM is across that cabinet or going through that cabinet, and you find that CFM with that model and speed tap, and you're extrapolating backwards. Is that correct?
Yes, sir.
I would say, why not? I've never tried that. Thank you for. I'm a little stumped today. That doesn't happen often. Thank you for that good question. I would say probably. Now the downside would be you wouldn't know if you did. You'd know what the CFM is, and you'd be able to extrapolate back as to what the speed tap you're on and the air handler. Obviously, you'd be able to observe that, but you wouldn't know how much static's on the supplier and how much static's on the return. So it would be valuable information, but there'd be no way of knowing what my supply static was and my return static. Now you could do something like this. If you know what the CFM is, and you could take the static pressure on the supply, whatever that static pressure was, whatever's left over has to be on the return, right?
That was going to be my next.
Yeah. So my comment would be, why not? I mean, if you know the CFM and you know one static pressure, then the other one has to be the other. That is a great field tip. Thank you for that. I think that I think I'm going to research that some more. But please do me a favor, when you get out there in the field, give it a go. And if that works really well and it can kind of give you some idea what's going on, please share that with us, because I'd love to include that in a training session, with some field experience out there doing that. But thank you for that. That's a great idea.
Yeah, I come from the northern market where taking static pressure was not an issue because we had the application that's been in all your illustrations.
Yes, sir.
But when we come down here to the South Florida market, it's the norm to have the filter be in the air handler itself, and that leaves us not much room. Like one of the gentlemen was saying, one of my colleagues here was saying earlier that we're only have access to the front of a lot of these air handlers.
Sure.
And it's really difficult to get the return static pressure. So therefore, a lot of the guys in the field are discouraged from doing so.
I got you.
And that ends up with the mess.
Well, and I think what you've just verbalized is a best practice for the Florida market, and I like what I'm hearing. Thank you for sharing that, because like I said, I've often struggled a little bit too on how to coach people doing this. If you have just an open return, you've got an air handler essentially, in a situation where you're just sucking from, just from the space with very little restriction. You might have a filter and a grill, but other than that, how do you really measure that accurately? And I like what you're saying. If I do a temperature rise and I can confirm my total airflow, and then come right back and hit it with a supply static, and then whatever's left over has to be my return static, right? I like that. That'd be a best practice in your area. Yeah. Thank you for that.
Yeah, thank you, man.
Yeah, good. Any other good questions or comments before we do one more airflow measurement as an example, and then we'll wrap up with final questions and comments. All right, fellas, so we're going to do a temperature rise method one more time. This is a 4-ton unit. And so we have the formula up there. In this second example, we have 241 volts. We actually measure 241 with the fan running and the heat strips cooking. And I measure, I clamp my amp clamp on there, and I see I've got 50.1 amps. So quick reminder, we take voltage times amperage. So 241 times 50.1. But hang on, we're not done yet. You multiply that times 3.414 to give us BTUs, output BTUs. So 241 times 50.1 times 3.414 gives me my output. And so if you kind of poke it in on your calculator there, you should have about 41,221 is what I have. So 41,221 is the number I've got. So you should be real close to that. Next step we're going to measure our supply and return air temperature. And so in our example here, we've got 92-degree supply air temp, 72-degree return air temp. And we find the difference. That's the delta T portion of the formula. So the difference between 92 and 72 is 20. So take 20 times 1.08, and that's going to give us some number. So go ahead and do that on your calculator. 92 minus 72, which should be 20, times 1.08. That gives us that next portion of the formula. So that should give us 21.6. I then take the output 41,221, and I divide it by 21.6 to kind of complete that formula. And then that gives us a CFM of what? So 41,221 on your calculator divided by 21.6 should give us a CFM on the second temperature rise method of 1908. So on a 4-ton unit, I see that, you know, I'm measuring a particular speed tap. I see that I've got 1900, little over 1900 CFM on a 4-ton unit. But now hang on a second. Sometimes you can blow too much air, can't you? And so, especially in your market down there in the Florida market, if you're blowing too much air across the coil, your humidity control goes in the toilet. So you want to be blowing around 1600, between 1550 and 1600 on a 4-ton unit at a nominal 400 CFM per ton. So in this example here, let's say I'm on speed tap number 5. Maybe it's a brand new install and the air handler comes from the factory on high speed tap for cooling. That's very common. You know, we do that on the Champion side because we don't know what kind of ductwork it's going to be installed with. So we always place our cooling tap typically on high speed. Well, you might have a really nice duct system. It might be a nice open duct system, well designed and so on. And you're on high speed tap, when you commission the unit, when you start it up, you notice that you've got 1900 and change for CFM. Well, you need to slow it down. So maybe you'll have to go to a medium high or maybe even medium speed on that particular duct system to give you your 1600 CFM or close to 1600 on that 4-ton unit. So again, guys, sometimes you can have too much airflow and you start having some humidity comfort issues, some latent or what we call humidity issues because you're blowing too much air. So please keep that in mind as well when you set up your airflow and you commission the unit, that we're looking for right at 350 to 400 CFM per ton nominal airflow when we set our airflow up on our duct systems. With that, I'm going to go ahead and pop the questions, kind of open the floor up for everybody. I'm going to go ahead and shut my PowerPoint or minimize my PowerPoint, and I'm going to open the floor back up here. Let me go ahead and get that PowerPoint shut down, and then let me get my camera back on as we open up the floor for any final questions and comments this morning. And let's see here. There's my camera back. Okay, good. So let's open up the floor for just a minute or two if there's any final questions and comments on our training and our overview this morning. And by all means, please open up your mics or hit that chat box, and we'll be glad to answer those questions as we kind of conclude our training this morning. Everybody good?
Well, guys, thank you very much
Well,
for
thank you.
attending. I want to add that Winsupply Port St. Lucie has established another one of these 1-hour training sessions with Joel, and it is going to be held at 7:30 a.m. Eastern Time on Wednesday, October 26th, and the subject is going to be microchannel coils. And
Yes.
Joel, you want to just kind of give a little bit of background on what you plan to cover during that session?
Absolutely, fellas. Let me go ahead and conclude. Thank you for training with me today. Let me go ahead and conclude real quick the airflow class real here. We'll go ahead and stop the recording on that.